like Professor Pao and Hsiung is working as a professor in the Department of Computer Science and Information Engineering at a National Chung Cheng University. He is also a director of Smart Living Technology Research Center and vice director in Taiwan India Artificial Intelligence Technology Innovation Center Research Center. He has received his BS degree in mathematics and PhD in electrical engineering from National Taiwan University. He has published more than 260 papers in top and reputed international journals and conferences. He is also a recipient of the 2004 Young Scholar Research Award given by National Chung Cheng University to five young faculty members per year. He has awarded with the 2010 Outstanding Research Award by National Chung Cheng University, where only three faculty members were awarded. His main research area are smart grid, smart traffic, driver fatigue prediction, landslide prediction, cyber physical system, and many more. Today he is going to take a session on real-time rain removal using a novel sensing GAN model. We are welcoming you, sir. And could you please start the session? Thank you so much.
Okay, thank you, Dr. Jugal, for the kind introduction, and thank you for inviting me to attend this FDP from RRU, and welcome one and all of you to attend this session. This session, I'll just share my slide first, and then I'll continue.
Sure, sir.
I hope all of you can see the slide. Okay,
Yes.
Okay, thank you. This talk that I'm going to share with all of you is actually the results of a master thesis from one of my students who just graduated this year. Actually, he just came to my office to sign the leaving the university, the form for leaving the university. Yeah, and I'm going to present his work. The reason I'm presenting his work is because he was one of the best master theses that I supervised in the last 2 years. All the professors who attended his VIVA oral exam gave a very high appreciation and high marks for this work. This work is something related to how we can improve our image processing or image analysis using deep learning technology. But before I go into that, as Dr. Jugal just described, I'm from National Chung Cheng University. I've been teaching for at least 20 years now in the Department of Computer Science and Information Engineering. My expertise is mainly in embedded systems. I was doing FPGA, SoC, NOC, a lot of hardware-related things before, and now I'm doing data-related, AI, deep learning, these kind of things, especially IoT and AIoT. As you can listen or hear from the accent that I have for the English, because I was actually born in India. I was born in Mumbai and grew up there, and then later on, after my high school, I came to Taiwan. So I'm quite familiar with India, and actually I also miss some of the things from India. I go back each year, but I've not been back for at least 2 years now because of the pandemic. I hope I can do so at least this year or next year. Okay, so let me continue. Real-time rain removal using a novel SensingGAN model. I'm not sure how many of the audience know about deep learning or about the GAN model. GAN means a generative adversarial network model. Actually, it's a two-model architecture. It has a model called generator and the other model called adversarial network or adversary. So these two models work together just like a student and a teacher. The student tries to obtain good grades in whichever subject the student is taking, and the teacher would like to actually give him more and more difficult questions so that he keeps on learning. So the adversarial network, or the adversary part of this two model architecture, is the teacher, and the generator part is the student. So a GAN model has become a very popular way of learning things, especially in the deep learning area. This was proposed, I think, around 5 or 6 years back. GAN model has taken a lot of applications across many different kinds of areas, and it has been very successful in improving analysis or recognition of objects, of patterns, of pedestrians, of human beings in the images. So we are in this work, we are trying to do one thing, is how we can remove the rain that is often found in images. The reason we want to remove, let me change my slide. Okay, yeah, you can see the change of my slide, because sometimes in Google Meet we often face the problem that the presenter changes the slide, but the audience cannot see it. Okay, now I've made sure that we are working. Okay, this is working. Okay, so let me show you two pictures. On the left hand side is a rainy day picture. As you can see, there are some cars on the road, there are traffic lights, there are some buildings, but everything is quite blurry. The reason it is blurry because there's rain in the image, and though the camera is inside the car, but the images still have rain. So when you're trying to look through the rain, suppose the rain is a small light rain, then of course I think even we people can see whatever is on the road. But if it is a little heavier, I mean, if the rain is heavier, or if there's more water in the image, then everything starts getting blurry. Once it is so blurry that sometimes even we human cannot see clearly what is in front of us, right? Not only for rain, sometimes also for smoke or fog. And sometimes if the camera is outside, this camera is in the car, but sometimes if the camera is outside, like a CCTV, on a CCTV, which is often placed outdoors, the lenses gets dusty. So lots of dust and dust particles collect on the screen, or on the lens, which makes the images quite blurry. So we often need a technique where we can remove the noise. We can consider these kind of things like the rain, the fog, the smoke, the mist, or sometimes if it is a little dark also, and we can also tackle for example, dust on the lens, on camera lens. So in this way, we need a technique where we can remove these kind of noises. Okay, but here in this work we are mainly focusing on rain, but of course you can always extend it to fog, to smog, SMOG, or for other dust particles. As long as there's rain, we can do this. Actually, people have also been using these kind of methods for restoring old pictures. Like suppose if you have an old picture of your great grandmother or grandfather, and of course you would like to have a more clearer picture of the clearer view of the photos. So we can also use AI techniques to restore the photo, so that I mean, whatever is on the pictures, suppose there's some yellow parts because if it is old, and or if there's some what do you call it, some edges which have been created because of the folding and etc. So these kind of noises can always be removed, or at least partially removed, if not all, so that we can get a clearer view of whatever we are trying to look at. You might wonder, what exactly is this used for? Okay, of course, if it is the first application that you can think of is autonomous driving. When we people are driving, if the rain is a little heavier, we use the what do you call it, the thing which is on the front screen, right? For wiping off the wiper, right? Yeah, wipers. Yeah, to wipe the rain. Okay, so we use that so that we can get a clearer view. But if it is very, very heavy, then of course we cannot see. So there's always a scope as to how the AI models can remove the rain. Of course, you might say that in autonomous driving, we can also use the wipers. But even with the wipers, suppose we want to remove something on the lens, then it's difficult. We do have lens wipers also instead of the car wipers, but that is still not very stable, or what do you call it, that much stable to be used. Okay, so this is the whole motivation of the work. On the left you see the rainy picture, on the right you see the de-rained picture. With de-raining, you can see some things are getting more clearer, like the edges of the road, the lane markings, etc., and even the car. Okay, so as you can see, this is the second slide. You can see the car is detected here. Okay, so on the right hand side in the de-rained image, we can detect a car. 0.54 is just the probability of it being a car. It is quite low, as we know. Sometimes it should be at least 0.8, 0.9. 0.54 is quite low, but at least we can detect it. But on the left hand side, the rainy picture, we cannot detect the car. I mean, using automatic detection. On the right hand side, because we have cleared some of the blurry parts, so we are getting a detection of the car, which shows the actual use of de-raining. But of course, not only the car, we can also for the other objects like the traffic lights, the pedestrians, these kind of things, we can always improve the object detection of whatever autonomous driving or the other areas you're using it. Of course, besides autonomous driving, actually these kind of technology can also be used in, like, for example, image reconstruction. So actually there's a whole course on image reconstruction. When we have images, like for example from the satellites, or from the space, whatever of the space or of any planets, or so sometimes we do need to reconstruct the image so that we can use our naked eyes to see what exactly was supposed to be on the in the image. So this is the main reason, and there's a statistics which shows that if we don't have bad weather, that is, if we have good weather conditions, we can do good detection of the pedestrians. But if the weather is bad, the detection of the pedestrians, the accuracy of detection goes down by 8.41%, which shows that actually pedestrians are less. I mean, it is more difficult to detect the pedestrians when we have rain. Okay, so this is one statistic which shows you that we do need de-raining techniques. Okay, there's another statistics which shows that 21% of car accidents are actually caused by weather conditions. 21%, and out of those, sometimes the car accident is not because of the weather conditions, it's because of the human the drivers or whatever of other conditions. But weather conditions account for 21%, which means out of 5 accidents, 1 accident is due to weather. And then out of all the accidents which are caused by weather conditions, 46% are caused by rain. So that means nearly half, which means around 10% of the total car accidents are caused by rain. So if you use de-raining, at least for autonomous driving, or even for recording whatever is happening on the, for example, we have vehicle recorder, right? We have recorder which records while we are driving. So if we have de-raining, actually we can also have a clear view of whatever is happening on the road. So these are statistics which shows that we do need de-raining techniques for autonomous driving. Okay. There are several existing work which has proposed different AI models for removing rain, which is called rain removal. But there are two kinds of rain, or at least two kinds of rain, where, in the data sets where we try to remove them. One is called raindrop, the other is called rain streaks. Raindrop means the rain which appears in the image are like droplets, rounded ones. But sometimes, because there's also wind, or because of the speed of the car, the rain does not appear like a drop, like a water drop. Instead, it becomes like a streak, a line, a streak of water, streak, streak of water. So it becomes rain streaks. So we have two kinds. Basically, in the data set, we have raindrops as well as rain streaks. So it depends on how good your model can do deraining. Sometimes it can be performing very good for raindrops, but not for rain streaks. Sometimes for rain streaks, but not for raindrops, and sometimes for both, you can do good. Okay, so here in this case, this is called attentive GAN, which was proposed, let me see, 2018. So that was around 3 or 4 years back. Raindrop removal was the main target, but as you can see from here, let me use my pen. Okay, as you can see from here, once the raindrop image goes in, there's a generator. There's a generator and there's a discriminator. So basically, it's a GAN architecture. Basically, it's a GAN architecture because there are two models which work together to learn things. The generator, as you can see here, they have several layers, like 5 layers of ResNet and 1 layer of LSTM. If you know deep learning, you might be knowing what is ResNet. But if you don't know deep learning, you can just think of it as layers of neurons. Okay, ResNet is actually residual network. Residual network means initially we used to have one layer by one layer of neurons. Instead of having so many layers concatenated together in one architecture, sometimes while we have reached the end of the architecture from the left to the right, though we have grasp the high-level features of in an image, we tend to forget the low-level images, the low-level features. We tend to forget the low-level features. So because of that, we need to do residual things. Residual things, that means we are trying to take things from the back to the front. Okay, from the past to the future. So by taking things like that, I mean, trying to actually, it's like a review. Like suppose if you have gone to your college, suppose junior year, third year, when you're giving some exam, or if you're sitting for the postgraduate PG entrance exams. I'm not sure what is the condition in India, but in Taiwan we have PG entrance exams. So you need to give PG entrance exams for different universities. When you're giving these kind of exams, they might test you operating systems, which you learned maybe in the second year, sophomore year, or maybe computer architecture, which was in the third year, something like that, or algorithms, or even linear algebra from the first year. So you need to revise, right? You need to revise things so that you can sit for the exam. It's similar like this. Residual networks are things that you keep on revising things so that you don't tend to forget things. Okay, so that is called ResNet. So RES stands for residual. LSTM is long short-term memory. Long short-term memory. L is long, S is short, term memory. Long short-term memory was proposed, I think, at least more than 1.5 decades. I think 15 years, or maybe even more than that. It was proposed long time back, but it has become very, 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 very popular. I don't think I've used too many varies, which shows that it is a very, very popular architecture because it can remember not only short-term memory, it can also do long-term memory. Okay, so long-term, short-term, it remembers a lot of things, and its learning is quite good, especially for time series data, which is data which has temporal characteristics. Okay, just like, for example, a speech, a voice recognition, or speech recognition. Anything which has, I mean, the data has time characteristics. Like the data now is quite related to the data 1 hour back. Or maybe even related to the data 2 hours back, just like the rainfall intensity, okay, or maybe the temperature, the weather temperature. The temperature cannot change abruptly at a specific location. It changes gradually, right? So there's always a time series in the data. So the data comes in a form of time series. This kind of time series can be learned, or we can do predictions for the data, for these kind of time series data, using LSTM. So these are very popular architecture. ResNet, LSTM, these are very popular things. At least they can be used as building blocks. Okay, so we often use them as building blocks. So this is a ResNet building block. This is an LSTM building block. So you can use multiple building blocks to create a neural network architecture which can learn things. So this is what they proposed, active recurrent network. So they have so many layers. You can see this whole thing is quite complex. There are so many layers, and then they get a attention map. Attention map means the map of where exactly is the rain. Actually, you can also call it the rain map. So where exactly is the rain? So that is trying to remove the rain. So of course, before trying to remove the rain, you need to know where exactly the rain is. Okay, so that is learning the rain. Where is the rain? Okay, and then the skip net is used to remove the rain, and then you get a derained image. And then this derained image is passed on to the discriminator. Discriminator is most often a set of convolutional neural network layers, which we often call CNN or convolutions. Sometimes it's coupled with max pooling or average pooling. So convolution is often coupled with pooling. Here it is ReLU. We have ReLU activation. I'm sorry, I won't be going into details of all these different things, because I'm sorry, this is not a very fundamental talk. It is more like application of neural network architectures to the rain removal application. Okay, so it's more application oriented, but I was afraid that maybe some of you might not have heard about convolution, about ReLU, about GAN, about ResNet, about LSTM. So I spent some time here on this slide to go into the details. But like, for example, what is FC? FC is fully connected. So fully connected means we have lots of neurons like this, one by one, which are all connected in one layer. Okay, so it's a big layer with lots of weights. In deep learning, basically when you are trying to train the model, the basic thing that you're doing while you're training the model is to learn the weights or to tune the weights, so that the weights can be used to actually grasp whatever it is learning. Okay, the patterns in the data. So when you are grasping the patterns in the data, actually you're tuning the weights. So this is called training of the model. Anyway, so this architecture, additive GAN, can remove raindrops, but it is very slow. As you can see here, it needs at least 0.2 seconds. The time here, you might say that okay, 0.2 seconds is quite fast, because it's not even 1 second. But as we all know, in a video data, in a piece of video data or a video clip, each second you might have actually 30 different frames. So you might have 30 frames. That means 1/30th. That is 1/30th of a second. You have a frame, a data frame. So if you can only process one frame or one single image in 0.2 seconds, that means in 1 second you can only process 5 frames or 5 images, 5 single images. That is quite slow, because you have 30. So that means out of those 30, you can only process 5 in each second. So the rate is 1/6 of the original video bit rate. Okay, 1/6. So that means you're skipping a lot of frames. You cannot process that quickly. You're skipping a lot. Of course, you might say, why do you skip? Why do you not process all the? Of course, if it is often offline, you can always process it. I mean, at ease. You can process it at ease. You don't need to hurry. But if it is an online system, like an autonomous driving, it is online. It is real time. In that case, that you can only skip. Otherwise, you won't be able to catch up with all that data. Because suppose if you go and process each and every frame, I think you will be lagging a lot behind the actual video that is coming into the system. So the driver might see the derained image of something which was a few seconds back, or maybe a few minutes back, and then gradually it might be a few hours back. I think that won't be of use, because then the car might just bump into something which was not detected because of the rain. Okay, because of the rain. So for autonomous driving, you need real-time characteristics of the or real-time implementation of the system. That means if you cannot process 30 frames per second, at least you should do 15. Right? Out of 2, you do 1. I think that is acceptable. Out of 2, you do 1, or at least in the worst case, you do 3. 1 out of 3. So maybe 10 frames. Yeah, so that could be making it more acceptable. But of course, if you can process all 30 frames in 1 second, that is all real time, so there's no problem, except if you have 60 frames per second. But normally 30 frames per second is quite good, so that is something which is acceptable. But 0.2 seconds is too slow. Okay. Yeah, so this is one architecture. Let me show you another architecture which does very well as far as timing performance is concerned. As you can see from here, this is called kernel prediction network, KPN, kernel prediction network. It has a very good timing performance of 166 frames per second. As I just said, well, once you get 30 frames per second, that's real time and that's good enough. But they are getting 166, which is much higher than whatever is acceptable. So 166 is quite good, but of course, then you have to check, does it give a very good deraining effect, right? Because sometimes there's always a trade-off between how accurate you can do something and how fast you can do that thing, right? So like suppose if you're hurrying through things, you're trying to hurry, you're trying to catch up, then of course you might miss something, you might do something which not as good as that. Like suppose if I only give you 2 days to learn a subject and give you an exam, compared to if I give you 20 days, of course you'll do quite well when you're given 20 days instead of 2 days, right? So when you have more time, you can do better. If you have less time, you won't be able to do that good. So they are trying to improve the timing performance. That is, they're getting 166 50 frames per second, but they're not getting a very good extraction of raindrops. I'll show you the pictures or the images later on. Let me go into the architecture first. This is KPN. As you can see, rainy image is coming from the left-hand side, and we are getting the feature maps on the right-hand side. You can see that there are several different layers called convolution, pooling, crop, upsampling. Okay, so there are different kinds of neuron related neurons in each layer. But the main characteristic of this architecture is a U-net. As you can see here, it has a U architecture in the shape of U. The reason for this U-shaped architecture is because actually U-net was proposed for medical diagnosis, okay, for diagnosing tumors, cysts, lesions, those kind of things in a medical image, like for example in the CT scan or in an MRI scan, okay, so or in a PET scan. So it was used for that, but of course you can also use it for raindrops here. Okay, so the U-net architecture is actually it has two branches. One is on the left hand side, this part on the left hand side, and you have another branch on the right hand side. On the left hand side, you start with a big image like this one. This is a big image, and then you gradually restrict the image, making it smaller and smaller in size, but making it more compact. Okay, so they are trying to keep the characteristics of the main characteristics of the main features of in the image in the data that we are trying to produce. Okay, so once you have reached from the top to the bottom on the left hand side, actually you already have a vector which represents all the main features in the image. Okay, like for example the raindrops, or maybe the buildings, the edges, whatever, or the car, the edges of the car, those kind of things, we can keep it in the vector. Okay, so this is a very compact representation. Whatever you're getting at the bottom of this architecture, this is a compact representation of whatever was in the rainy image. Okay, but then you will also ask the question, why do we need the other branch? Okay, the other branch is actually trying to enlarge the compact vector that you got, the compact representation, enlarge it into the original size of the rainy image, okay, so that whatever you can see in the final output is actually the same size as the rainy image, but it is a derained version of the rainy image. Okay, so you have removed the rain. So this is something which you can do, or maybe not exactly remove the rain, because here we are not removing the rain, we are trying to keep the features. Okay, keep the features and trying to point out where exactly are the rains. So whatever rainy image you're getting on the left hand side, on the right hand side you get the same image, same size, but it tells you where the rains are. Okay, so this is a map. Actually it's a rain map of the original rainy image. Yeah, so That was one, and then people also produced another. Proposed another architecture called SA module. SA is self attention. Self attention. Self attention here. Self attention has become a very popular technique in the past 1 year, 1 or 2 years. But it has become very popular technique. In short, it is called SA. Full form, it means self attention. Self attention is something like this. You try to compare your pixels with your neighboring pixels. Okay, so you do a lot of comparisons across the pixels, so that you know that whether you are quite related to your neighbor or you're different from your neighbor. Okay, so self attention is something which can make the edges in the images more precise, more clear, more clear cut. Okay, so these images, because the image has already been made blurry because of the rain, after you remove the rain, you would like the edges to be very clear. Okay, you don't want the edges to be blurry, because our human eyes are very sensitive to edges. We are not very sensitive to gray areas. Some changes in the gray areas, we are not so sensitive to that. We are not so that they are not so distinguishable to our eyes, but the edges are very distinguishable. We often, like for example, when we are looking at something, we first look at the edges. So the edges are very important. The edges of the car, the edges of the road, the edges of the tracks, the edges of the sky, the edges of the horizon, the edges of the traffic lights. So these are all very important features, which once we get a clear edge, the edge is a clear cut or a clear line or a clear circle or a clear geometric shape in the picture, then you think that the image is quite clear. Okay, but if the edges are blurry, then you think the image is quite foggy, quite blurry. Okay, so this is self attention is mainly used for making the edges more clear. Okay, and there's one more technique called dilated convolution. Dilated convolution is like this. Suppose you have a 3x3 image data. So we have nine pieces of data or 9 pixels. It depends on whether you are working with 2D or 3D. Here it's 2D. If you are working with 3D, it's 3x3x3, in which each data is called a voxel, right? VOXEL. But in 2D, it's called a pixel, PIXEL. Okay, so you do a dilution or a dilation. Actually, it's called a dilation. Okay, so dilation means you're adding zeros in between the real data. Okay, you're padding them in between, not from the side, because normally when we say padding, we are padding something from outside, right? The last row, the first column, the last column, that is called padding, adding zeros. But now we are doing dilation. This is not called padding, this is called dilation. We are adding zeros in between. You might ask the question, why do you want to do dilation? Okay, why are you dilating the original piece of data? Won't this data become blurry, right? Because you're putting so many zeros in between. The reason is sometimes when you're doing object detection, what happens is the objects become very, very small. You might ask that, okay, the camera resolution is quite good, I don't need dilation. But irrespective of whether the camera resolution is good or not, sometimes what happens is the object is very far away from the camera. Whatever good camera you have, the object is quite far. The object is so far that it appears very small in the image. When it appears very small in the image, the number of pixels that represent the object is very small. Okay, it's a small number of pixels. Then it's very difficult for that to detect that object. Suppose it's a small motorbike, or maybe it's a small car which is very, very far away. So big cars, you can always do object detection. There's no problem. Big people means the people that are near the camera. But if the people is very far, I think I can share a real experience of this thing. When we were visiting a hospital in Taiwan, we have hospitals for which we have installed fall detection systems. So what happens is, when we have installed the fall detection system, when the person is quite far away, like in a long corridor, if the person is quite far away, he is very small in the image. So we cannot detect he has fallen or not. okay, because he's quite small. And if he is very near the camera, then of course we can always do very good fall detection. So the problem is the object is too small in the image. So dilation is a method where you can enlarge the object so that instead of being a 3 by 3 object or a 3 by 3 pixel representation of the object, it becomes larger. Like for example, here it becomes a 5 by 5, right? Though it's quite blurry, but at least larger. And here this is even larger. Okay. So this is a method which has improved the detection of small images or small objects. I'm sorry, small objects. So far vision convolution. So we call that far vision convolution. Means that the camera is the object is quite far from the camera, so we can do far vision. Okay, that was a brief account of what people have been doing in the past. Let me give you a full summary in this table of all the works, at least the state-of-the-art works in this area. This is a very good survey of rain removal. So if you are interested in rain removal, actually this table would suffice. It's sufficient for you to go through all the main techniques. So this student, Mr. Chen, he has done a very good job in surveying all the state-of-the-art models. So you can see here on the left-hand side, we have JORDER, which was proposed in 2017. And then we have DID-MDN, efficient D-RAIN, unit transformer, SR-GAN, attentive GAN, SA-GAN, IDC-GAN. These are all methods which have been proposed. Like, for example, these two were proposed to this year in 2021. This was proposed in last year, 2020, and then some were proposed in 2018, 2017. So this is a very good summary of all the works in this area. Some have been focusing on rain removal. Some has been focusing on super resolution. Super resolution means making the image of a higher resolution. Okay, so D-raindrop or image generation, there are different focuses, and we have different structures here. Loss function characteristic. What is a loss function? A loss function in deep neural network architecture is mainly a function where you can estimate how much is the prediction different from the original ground truth. Ground truth means the original label or whatever the original truth was. Okay, so like for example, in this case, in this application, how much is the derained image? I mean, what is the difference? Okay, how much is the loss between the derained image and the original image? Not the rainy one, the original one without the rain. Okay, so if you compare that, and if you get a very small loss, means you have learned a good. You have done a very good learning, and and the deraining was quite successful. Okay, but if it is big loss, that means the deraining is not good. So we have different loss functions which can be used here. So like perceptual loss, SSIM, etc. And then we have the characteristics of each model here given on the right hand side. I won't have time to go through all the different works, but those which have been put in red here, like for example KPN, L1 plus SSM, efficient, these are the works which we have actually considered either referencing their architecture into our architecture or comparing with them. Okay, so these are the main the red ones are the main structure or loss function or characteristics which we have compared with. Okay, so efficiency is quite important because we have applications which are real-time, like autonomous driving. But of course, there are different kinds of rain, as we just said, rain streaks, raindrops, and then we need to restore the edges, the details of the objects, so that we can do good object detection. Okay, so rain removal or deraining is not the end of everything. It is just a step in between. It's one step of the procedure. The actual goal is not deraining. The actual goal is object detection. Okay, we want to improve object detection so we know what is on the road. Okay, what are on the road? What is in front of me? Is it a car? Is it a man? How big is the car? How far is the car? Is there a traffic light? Is the traffic light red, green, or yellow, or what? And then I mean, you have to know everything on the road, right? So that is called object detection. So in that case, you need to have an accurate object detection. That is the final target, the final goal. So deraining is just only one step before you do the actual object detection. Yeah. So we need to do a rain removal method. Okay, rain removal method. We need to find a good balance point between efficiency and performance. Right? Just like when you're studying for something, suppose you're going to sit for an exam and you only have 2 days. Of course, you would like to make the best use of the 2 days, right? So that you can get the highest marks in that exam. So this is often a trade-off of how you're going to use the time so that you can perform good as well and get a good performance, right? I mean, do it fast, and as well as get a good grades. Yeah. So these are the main goals. We have proposed a lightweight GAN for real-time rain removal. We have used self-attention. We have also used something called as a SA feature loss. I'll show you the details later on. Okay, I'm going to skip some of the math, but of course, if you're interested, we can always talk about that later on. Let me just talk about this one equation. The rest of the equations, I'll leave it to all of you. The raining image is actually the ground image. Ground image means the image which does not have the rain, and then the positions of the rain and the effect of the rain, right? Whether it's a drop, it's a streak, whatever. Okay, so once we have applied this, these kind of noises, so actually this is a noise, right? This is a noise on the original image. Then you get the rainy image. So this is just a mathematical definition of what exactly is a rainy image. Okay, so a rainy image is an original image plus the noise, and the noise depends on the for example, the effect of the rain. E is the effect of the rain, which means that either it's a drop or it's a streak, something like that, and the positions of the rain, where exactly the rain is falling, right, on the image. Yeah, so I'll skip all of this. I'll just go directly to the okay, so these are some preliminary assumptions. I'll also skip this. Let me go directly to something which is more appealing to the eyes. Otherwise, I think most of you online might be already dazing off. Okay, sleeping. Okay, so here let's first define our scope. The first one is blurry. So you can see the rain is very heavy, right? We have a very heavy rain. It's so heavy that it's very difficult to actually remove the rain, right? So we cannot handle this kind of thing. If it is a clear image like this, the road is wet, but there's no rain actually falling now. So there's no need of any rain removal. But here in this case, this is the case which we are actually handling. We do have some rain. It's not very heavy, and of course we need to remove the rain. Like suppose if you remove the rain, maybe you'll get a clear image of what exactly is the number, the car license plate on the car in front of us, right? So that is something which might be useful. So this is something which we can handle. Okay, the raindrops. Okay, we can remove the raindrops. Okay. So we are going to use different kinds of architectures, methods, and all. Okay, let me show you the actual GAN architecture which we have proposed in this work. So what we are doing is we are trying to propose an efficient generator with a discriminator. Okay, the efficient generator has two parts. One is in front, this part, and the other is at the back. These two parts they both appear quite same. They are both U-nets. Okay, they are both U-nets. You can see here, this is a U-net. This is also U-net. Okay, they are both U-nets. The first U-net, this one here, the first U-net is called SA U-net or self-attention U-net. This is used for extraction. Okay, rain feature extraction. So after you have gone through this unit, the rainy image which we have put into this architecture, after going through this architecture, you're going to get a feature map. Whatever you're seeing here in gray is actually the locations and the intensity of the rain. Okay, so it's a rain map, a map of where the rain is located and how heavy is the rain in each part. Actually, is in each pixel. Okay, so deraining. So this feature map is very similar to what we are doing in medical diagnosis. So medical diagnosis, you're often concerned with which pixel is in the background, which pixel is in the tumor, or which pixel is in another kind of tumor. Sometimes you have malignant tumor, you have benign tumor, right? Different kinds of tumor. So similar here, which pixel is the background, which pixel is the rain. So you have to make sure of this. The second one is called SA SkipNet. This is also UNet. This is also UNet, as you can see from the architecture here. What it does is this is doing the actual rain removal. Okay, so once you have the rain map here, you are sure of where the rain is and how heavy is the rain per pixel. So because of that, and because you are also reading the original image here, as you can see from this arrow, you're reading the original image along with the rain map, so you can remove the rain. So this is the derained image. As you can see here, most of the rain have been removed, right? So this is what we proposed, and this is much simpler than KPN, which was not KPN, attentive GAN. This is much simpler than attentive GAN, so it's quite faster. It's faster. We can do it actually in real time. I'll show you the details later on. We have a discriminator. We didn't have any innovative approach here in discriminator, but we had in the original generator architecture, we had 2 units, and then what we did is we applied self-attention also, and we proposed new loss functions also. Okay. Let me show you what we did. Like, this is the first UNet architecture, the first one, which gives you the feature map, as we have seen before. The innovative part here is we added a self-attention, this one, SA, self-attention module or layer at the bottom of the unit. But the question here is, where do you add it? Okay, do you add it in front, somewhere in between, or at the end of the bottom? Okay, I'm talking about the bottom of the unit of the U architecture. So this is the SA module. Do you add it in front or do you add it in back? Does it make a difference? These are all the research issues that research questions that you would like to answer when you're doing this kind of research. Then we have the deraining module, which actually removes the rain. So this is the second unit. Okay, so it's still a unit, but it's the other unit at the end of the generator architecture. I cannot find my. Okay, this one. Yeah, this is also a unit, and we do have a self-attention module again here, right? As you might have noticed, in the front here, in the first module, in the first extraction module, the SA was at the back. Okay, the SA was at the back. Okay, at the end of the bottom, and then in the SkipNet or in the deraining module, this self-attention is at the front. So this is in the front, and this was at the back. Okay. Later on, I'll show you some experiments where we do different combinations of the self-attention module, front and back, back and front, and then we can see what is the difference. Okay, this is the discriminator. It's very simple. It's just a layer of convolutions, and then we have 2 fully connected layers, these 2, and then we have a sigmoid function, and when we do the final analysis. Okay. For the loss function, this is a very simple log loss. If you're familiar with deep learning, you know what's a log loss. Basically, it's a function to estimate the error. Okay, the error in prediction or the error in deraining. So that's why we have a difference between the original image and the generated image. Okay. As far as the generator loss is concerned, we have 4 parts. One is for the generator loss, the other is for GAN, and one more is for the Euclidean distance, which we use L1 distance, and then we have SSIM, structural similarity. This is for luminance and contrast in structure of 2 images. Okay, so these 2 losses, the last 2 losses, are actually to make sure that whatever picture, whatever image you're getting at the end of deraining of the deraining procedure, it looks very similar to the original one. Okay, irrespective of whether pixel wise, like L1 you're doing pixel wise, this one, and this is you're doing also pixel wise, but this is more in the area of contrast, luminance, and structure. Okay, so whatever picture you're getting, you don't want to have any color shift. Okay, you want to have the color same as the original one. You don't want blue things to become red or red things become blue, right? So of course, this is just a very extreme example. You won't be actually having this kind of example, but I'm talking about shift in color. So you don't want to have color shift, you don't want to have the pixels quite different from the original image. So that's why we do this kind of loss function. Okay, loss function consideration. A loss function is something which we, when we are learning deep learning, you have to take care of. You have to make sure that the loss function is something which targets exactly what you want. Okay, so you actually you can design your own loss function for different architectures. We also used feature loss. Feature loss, we used VGG16, which is a very popular architecture for feature extraction. Okay, so like for example, if you're familiar with some of the new architectures like OpenPose, if you're familiar with OpenPose, or any other architectures where they need to extract the features in the image, they often use some of the front layers of VGG16. VGG16 means it has 16 layers. Like here, this is 16 layers. This is VGG16, and we can use a part of the front layers like 10 or 11. Okay, often the some of the front layers, they are used by other architectures, mainly for feature extraction. Okay, so this is one thing which we can take a note of. As far as SA feature is concerned, we are trying to use some of the low-level features as well as one of the high-level features. Okay, so we are trying to combine these two. Often is the case that when we only look at the high-level features, we don't remember the low-level features, or we forget, or we don't have information of the low-level features. And of course, we cannot only go for low-level features, because then you won't be able to know what exactly is in the image, right? Is it a car, or is it a truck, or is it a motorbike, right? Suppose these things look alike, they're all vehicles. You want to distinguish between them. Of course, you have to look at the high-level features. But sometimes, suppose this car, besides being a car, it also has some edges, like for example, the wheels, or the body of the car. So it has some low-level features also. I mean, the edges, right? The edges are the low-level features. You don't want to forget about the low-level features, because otherwise the car will be blurry, right? The car will be blurry. It will look like a car, but it's quite blurry. Then that's not something which we human eyes accept, right? We only want to look at things which are very clear, which are concise. The edges are sharp. You don't want the edges to be blurry. Whenever we are looking at something which has edges blurry, you're not so comfortable with such kind of image. So you want these things to be clear, right? So that's why, besides the high level features, sometimes you want to keep some low level features. So this is the combination of low level features and high level features. And my student, he has developed the SA feature loss, which means that we are trying to compare these two. I'm sorry, not compare. We need to combine these two and then do losses like here, right? So this one is this layer. This one is about this layer. This one is about this layer, and this one is about this layer. Yeah. So all of these losses are added together to make sure that we have high level features. There's no loss in the high level features, or very less loss in the high level feature, and less loss in low level features also. Okay, so we want to know that it's a car, and we also want to make sure that the car is quite good looking. I mean, good looking means the edges are concise, the edges are sharp. Okay, so this is we don't only want to, if you keep only the high level features, then you will be making sure that it looks like a car, but it's quite blurry. Then that's not good. Even after deraining, you don't want, of course you can say that because of the rain the edges are blurred, but still you want the edges to be clear, right, after deraining. So that is why we are putting low level features also. Okay, so we did lots of experiments with whatever we proposed, the architectures and all. Actually, this student did a good job, because he not only experimented with GPU servers, he also experimented with embedded system platforms like NVIDIA Jetson Nano. Okay, NVIDIA Jetson Nano is a very small platform. It's quite small in size, I think a little bigger than a name card. But it has very powerful ARM cores. It has GPU, NVIDIA GPU. So it does quite well. But of course, it's not a fully fledged GPU architecture inside. So of course, it will be much weaker than a full-fledged computer. Or full-fledged GPU. So, but it is often used for embedded systems, or even for edge AI. Okay, so many startups, they often use Nano for edge-based computing. or edge-based AI. Okay, edge-based means at the edge of the network, means at the location, wherever the application is, the AI application is being deployed at the location, not in the cloud. Okay, at the specific local site. At the specific local site, you put a nano, you put things there, and you put an inference model. Inference model means you put an AI model which has already been trained, and it is currently only being used for inference, not for training. Inference can be done in Jetson Nano, like face recognition. It's always possible in Nano. Actually, we have not only done face recognition, we have done open pose, not open pose. It's a lightweight version of the open pose called TRT pose. So we actually have TRT pose working. TRT pose is a version of the open pose which can work in embedded systems. We are using TRT, the accelerator for making things faster, or making things smaller. So TRT pose is a
hello everyone, I'm back and hope you're back too. So as far as the computing device was concerned, we had experiments being conducted on GPU server as well as NVIDIA Jetson Nano. So as I just mentioned, one has a very big or very powerful computing environment. The other is quite limited. We considered 4 different data sets. One is called RAIN 100H. The other is RAIN 1400. As you can see from the type here, let me change my pen. Okay, from the type here, we have, this is for the heavy rain. Okay, I'm not sure why the pen is not coming. Okay, heavy rain, and then we have low and medium rain streaks. We have raindrops. This consists of both rain streaks as well as raindrop. And something special about this is it's real data and it is rain in driving, which means actually we can do object detection also using this data set. These are the number of images that we use for training. There's a number of images we use for testing. Okay. So we did, the maximum image size was 512 pixels. This is the values of the different hyperparameters, like learning rate 0.002. For the Adam optimization, beta 1 was chosen as 0.5, beta 2 was chosen as 0.999. So these are all hyperparameters which you have to decide before you train the model. We generate a loss, lambda was 0.2 and omega was 1, and then we use the testing data set. The metrics that were used for evaluation consisted of frame per second, which is for speed, the peak signal to noise ratio, PSNR, which is a very popular evaluation metric for checking what is the difference between a processed image and an original image. So whenever we want to check the difference between two images, we can use PSNR. So if PSNR is very big, like 30, 40, then that means the images are very, very similar. And then we have the structural similarity index measure, SSIM, which is in terms of luminance, contrast, and structure. So SSIM is more often used for checking the difference in color or the color shift or the texture, these kind of things, more deeper things. So SSIM uses for, especially for the channel-based differences. Channels means the red, green, blue, these kind of different channels. And then we have the mean average precision, which is used for the accuracy of object detection. So I won't go into details of these different metrics. I think you can always get the definitions of these metrics online. Okay, so we did several experiments. Initially, we started with ablation study. Ablation study is for checking which part of our architecture or whatever innovations that we proposed, which innovation gave the best contribution or gave the biggest contribution. So that is called ablation study. So in deep learning, we often need to do ablation study, because with ablation study, then you're making sure which part of your research or which part of your innovation is contributing the most and which is contributing lesser. So we did this kind of ablation study, both for raindrop removal as well as rain streak removal. For raindrop removal, we use raindrop data set. For rain streak removal, we use rain 100H. And then we checked how SA feature loss is performing. This is a loss function. And then we did a comparison of our rain removal method with other methods. Okay, so this is the data set that we used. And then we finally conducted an experiment on the NVIDIA Jetson Nano also. Okay, so let's see. As far as raindrop is concerned, for raindrop, you can see this is the rainy image on the left-hand side, the original rainy image. There are two images here. And then this on the right-hand side, on the extreme right, you have ground truth. So ground truth is the actual image without the rain, so this is with the rain on the left-hand side, and the right-hand side is without the rain. And then in between, we have different versions or configurations of our architecture. The final one is called SensingGAN, but we start with more simpler ones, and then we add something, and then we add something, and then we add something, and finally we get this version. Okay, so on the right-hand side, this version, the second last is the fully complete architecture. So as you can see, for the ones which have lesser components or lesser architecture innovations, like suppose that we only use UNet without the SA, without the self-attention, you can see the performance is quite poor. The raindrops are still on the images, so they have not this. So using a very simple UNet or the original UNet, it's not possible to do any kind of deraining. But once you have added self-attention, you can see that there's a large difference between these two, right? These two. But still, like for example, here you can see there are some raindrops, right? So even with SA, we are still getting raindrops. So because of that, we used one more UNet called SA SkipNet, and you can see now the rain has completely been removed. Even here, something is quite blurry here, but we have removed everything, and this is a better version. So with two UNets, one is called SA UNet and the other is called SA SkipNet, and of course the SSIM loss function, we are getting a good result, but there's still a problem with the edges. Like here, as you can see here, this edge, okay, this edge is quite blurry, and here also the roadside edges are quite blurry at the roadside. So when you have blurry edges, we tried to use a loss function called SA feature loss. We added some more loss function to make sure that we are getting more concise and more sharp edges. So after doing that, we can see that we are getting a good result. So this is the final result that we are getting. As far as numerical results are concerned, you can see PSNR. For PSNR, the original one, I mean, the first version gave us 22.8, and then by adding SA, we had a very big increase in PSNR of at least 10%. So that is 25.2%. That is for PSNR, and then some more increases, but much lesser, and then finally we got 26. Okay, so that is the PSNR value. For SSIM, from 0.8 we increased gradually, as you can see, gradually, and then finally we reached 0.8614. FPS, because initially for the first version, the computation is much lighter because we are not using too much of what we proposed. So of course we are getting a high frame per second of 144. But once you add more and more things into the model of course becomes slower and slower because the computation has become heavy. So 94, it has reduced to 94. Then of course, because we are only adding some lesser things, and then finally we even increased to 98. Okay, so from 144 we had a decrease of, I think, 40 or 50 frames, and then we reached 98. 98 frame per second is still quite acceptable because it is much more than what is generally acceptable, like 30 frames per second. Okay, so that was one example. Let me show you another example from the Rain 100H. This is from a different data set. This is raindrop. This is from Rain 100H. As you can see here, this one, and this image, both of these images are rainy images, and the ground truth, just like the previous slide, these are clear images without any grain. And these are the results that we are getting for SensingGAN. Okay, and similarly here in the front, these 4 versions, before the SensingGAN version, we have the similar versions which have for which we have removed a part of the network innovations that we introduced into the final architecture. So this is called ablation study. We try to remove some parts, and you can see here in the previous what do you call it? In the previous data set, we had a big increase in PSNR at this stage. But now we can see that PSNR, the increase is rather at the end. Okay, so the increase is rather at the end. So this is because we have added the GAN architecture. So the difference between these two, this one and SensingGAN, is this is a very simple CNN-based architecture without GAN, and without the discriminator. This is with the discriminator. So SensingGAN with the discriminator, we are getting a high percentage of increase in PSNR for this data set. And then frame per second, we are also getting a real-time performance. Okay, so these are the 2 data sets. And then this is for checking the color shift. Okay, so this is for making sure that whatever deranged images that we are getting, the color in the final image is similar to the color distribution, especially the color distribution compared to the original one. So you can see that once we have, this is the ground truth. So these are the color distribution, or the color shift in the original image, ground truth image. And then this is one of the models that we applied, like the UNet and the SkipNet, everything. Okay, everything together without comparing the GAN part, the discriminator part. So you can see that these two are quite similar. And this has a large difference. So this is not working good. But after we added SkipNet, so you can see that with 2 units instead of 1 unit, this is only 1 unit, and this has 2 units. With 2 units, we are getting a good color distribution similar to the original ground truth color distribution. Okay, so the second unit has its effect. Here also you can see from the images itself, this is quite different from this one, and this is appearing more similar. Okay, you can see from, let me check, from the color. Actually, it's from the color, like the color of the cheeks. Okay, like the color of the cheeks, or maybe even the color of let me check. Okay, yeah, the color of the cheeks. Okay, so here also, because of the second unit, we are getting a better color matching with the original one. Okay, and then this was an ablation study of where exactly we should put the self-attention module. Because my student, when he was giving his viva, one of the professors in the review team asked him, why have you selected self-attention module to be placed here, back and front? Okay, so this was what he proposed in his work. Okay, so why is this the case? Does this give the best performance? That was the question. So he said, yes, I've tried all kinds of combinations, and this one is giving the best performance. So as you can see from here, he tried with front, back, front, back. Okay, so these front and back are actually talking about the 2 units. So we have multiple blocks at the bottom, like for example, 4 blocks here, 4 blocks here. So about the front and back, this is the front, this is the back, and this is the front, this is the back. So given the 2 fronts of the 2 units and the 2 backs of the 2 units, so of course we'll have 4 different combinations. So out of the 4 combinations, he got this one as the best, though I don't think there's a big difference actually. So you can see for PSNR there's a small difference. For SSIM also there's a small difference. So actually the location does not have a big effect on the actual effect of SA, of self-attention. Okay, so now we are talking about the SA feature loss, the feature loss which we added here into the architecture. As you can see here, this is the original perception loss, and then we change it into SA feature. We saw that by changing into SA feature, let me check why these two are so similar. Okay, there's some problem here. Okay, I have to check what is the problem here, because these two look very similar. I'm sorry, this is 19 and this is 16. I'm sorry, this is 19, this is 16. Okay, yeah. So so you can compare these two actually. Okay, because these two are VGG 16. This one is VGG 19. Okay, so for VGG 16, you can see that we do have an increase in the PSNR value, as well as, but no, for SSIM, I think we are instead having a decrease, but it's quite similar. So given the discriminator, when you add the discriminator, we are getting a higher PSNR and the SSIM. So we think that though the difference in PSNR and SSIM as compared to the one without the SA feature loss, instead of using the perceptual loss, if we use SA feature loss, as far as the PSNR value and the SSM value, these two values don't differ much. But when you look at the images, it's more comforting to the eyes, because the edges are more clear, concise, and sharp. Yeah. So let me show you some more examples of this is what we just saw. That was the numerical results. These are the actual image results. You can see from here, this is the perceptual loss combined with VGG 16. Okay, and this is SA feature. So this was the rainy image. This is the ground truth. Okay, this is for VGG 19. Okay, you can see that when you look at these two white colored boxes, you can see that with SA feature, some of the raindrops are much more lighter, or the blurry parts which have been created because of the rainy image. After removing the raindrops, the blurry effect has been reduced. Okay, so there are still some rain effects, right? These are the blurry parts which have been introduced, but here in this case you are having much more. Okay, much more. Like for example, especially when you look at this part. Okay, so we are having something better than the perceptual loss. Yeah. So this was for the perceptual loss. These are some numerical features, as we can see here. Okay, and this is also for this was for omega 1, and this is for lambda 0.2. So these are different parameters which we used for the SA feature loss. Okay, and then let's look at the results of our work with other work. Okay, other deraining work. Okay, so for efficient derain is the one which was getting 166, but we ran it for 148 frame per second. So it is very, very fast. But as you can see, there's almost not much rain removal. So this is the actual result we got when we trained the model, and we got the result. For attentive GAN, which is quite slow, as you can see here, it has only 7 frames per second, but it does a quite good job, right? So this is a very good job because the rain has been removed. As you can see from our work, we have also removed the rain, and we are getting quite a good efficiency. So we are getting 98 frames per second. So this is what we call as trade-off. We have used up some of the frame, or some of the frame per second, or some of the speed. We have compensated some of the speed for accuracy. So you can see the accuracy has increased. Okay, the accuracy has increased. We are getting a higher PSNR. We are also getting a higher SSIM at the expense of some frame per second. Okay, some speed. Okay, at the expense of some speed. But 98 is quite good. I mean, it's real time. So as you can see, we can do the real time deraining. Okay, so the main contribution of this work is real time deraining. Okay, this is another example. What we talked about here, this was the raindrop data set, and here is the rain 100H, which is heavy rain. Okay, so in heavy rain, we are comparing also with the efficient derain. and some other work which is targeted at heavy rain. So with our SensingGAN, you can see that we are getting a very high PSNR, we are getting quite good SSIM, and we are getting a very high frame per second, right? So we are winning in all these three factors, and that means we are also quite suitable for deraining in heavy rain conditions. Okay, so here that was the average performance, right? Now let me show you all one example. Okay, one example. So this is the rainy image on the top. This is the rainy image, and this is the ground truth. So this is the image without the rain. Efficient derain gives you good result, but something gets blurred. Yeah, the bridge here, the over the river bridge, and the stick that is coming out from, I think this is the sail, right? The sail post. Okay, the sail post of the ferry is getting blurred. We're not seeing it anymore. It's quite getting. I think it's disappearing into the sky. Okay, and for Jordan, another quite good deraining module. You can see that there are some extra streaks remaining, but for our SensingGAN, you can see that we have not only removed the rain, we have preserved the white post of the ferry sail, the sail of the ferry, and we have also made the bridge also quite clear. Okay, so this is quite good result after deraining. That was for heavy rain. Now for medium and low rain, we are not performing as good as the efficient derain. Yeah, so which shows that, but of course we are still getting real-time performance, and we are getting good PSNR and SSIM, but we are not topping the whole list. We are second to efficient derain. But you can look at the images and judge for yourself that actually whatever you are seeing here at the bottom right, this is our results, and whatever you are seeing on the bottom left, this is the result from efficient derain. Actually, there's not much difference between these two results as far as our eyes are concerned. As far as our naked eyes are concerned, I think they look quite similar. They've both done a very good job in deraining in the case of medium and low rain. So after deraining, efficient derain and SensingGAN has produced similar results. But of course, as far as the numbers are concerned, we are not top of the list. We are only second. Yeah. So that was about rain removal. Now let's move on to object detection, which is the actual goal of deraining. So after deraining, we do object detection. Normally, what we would expect is when you have removed the rain from the image, the object detection should be much, I mean, the accuracy should be higher, right? Should be higher than the one which was done for the rainy image, right? So, okay, so let's see what happens when we do the deraining and then we do the object detection. Okay, so we compared the MAP, mean average precision. We also compared the frame per second. So before the rain, the object detection was before rain removal. I'm sorry. Before removing the rain, we had an object detection accuracy of 44% in terms of mean average precision. Okay, so mean average precision normally around 50% is quite good. 40-50% is good. So 44% is good, but we can still improve. Efficient derain, we are getting 44%. Jordan, we are getting 46%, which is quite good. DID MDN, we're getting 42. IDC GAN 41. Attentive GAN 44. But for SensingGAN, which we propose in this work, we are getting 47%. So this is topping the list, and we are getting very good object detection. But of course, we are Jordan is almost same as us. They are getting 46%, and they have a very good performance also. They have a very good performance also. Okay, frame per second. Yeah, we are getting 56 frame per second, which is real time. Okay, so after if we do an averaging, on average, we are having a 3% increase in object detection. Okay, in object detection accuracy. Okay, that was on GPU. If you implement it on NVIDIA Jetson Nano, of course, you would expect a much significant drop in frame per second in the speed. in the speed. So for 32 by 32 image size, we are getting 16 frames per second, and then for even larger sizes, we are getting lesser and lesser. Okay, so this was just to compare how the speed decreases because of implementing it or having it inferencing on the edge. Yeah. So this is just some figures showing the differences between the different components. This slide gives you a whole summary of whatever we did. So here for raindrop removal, you can see raindrop removal, we are getting the best results. For heavy rain, we are getting the best results. For medium and low rain, we are getting the second best. The best one is still for efficient D-rain, but it is almost the same. We are second. But for rain in driving, we are getting the best results for as far as the accuracy is concerned. But of course, we don't have as much speed as, for example, Jorder or efficient D-rain. So that was a summary. Okay, so let me conclude this whole 2 hours session. We talked about self-attention. We talked about GAN. We talked about how we can use these models, for example, 2 UNets to get very good rain removal by extracting the rain feature first and then removing the rain from the rainy images to get derained images. And then using that derained images, we can do object detection. The accuracy increases by 3%. So that was all that we did in this work. And we did refer to a lot of work here. These are all the references. You can look it up. So if anyone is interested, I would be very happy to share with you the master thesis that of the student who just completed this work. You can work further on this work. Actually, I think he did a quite good job in this case. And that's the end of my presentation. You're welcome to present any questions you have. Thank you.
Thank you so much, sir. We are having one question, that is how to create rain data set and how to get GT in real time.
Okay, the first question regarding how to create a rainy data set. Actually, there are two ways in which you could get rainy data sets. One is by synthetic methods here, like these two, rain 100H and rain 1400. These are synthetic data sets. And the other two, raindrop and rain in driving, these are real data sets. Okay, so there are two ways. One is either you synthesize the rainy images from images which don't have rain. The other is getting real images of the raining conditions that you see normally in the outdoors. For synthetic data or synthetic rainy data set, there are many papers. You can look it up. There are many papers which discuss how you can create raindrops, how you can create rain streaks, and actually you can also randomize the location of the raindrops. You can also specify how large each raindrop is, how big each rain streak is. So there are many parameters which you can fill, and you can create new synthetic rain data sets, rainy image data sets, or you can get real data sets also. So there are many ways in which you can get rainy data set. But of course, instead of creating your own rainy data set, I would recommend that you directly download these data sets. As you can see here, these are all available on the internet. So you can always download these data sets and try your model. And then after you have done the basic training of the model, and then you can apply it to your real condition. Like for example, suppose you have rain and during the night. Yeah, so that is another big problem, because in the night or in the evening, the sun is going down and you don't have much light. The day is getting darker, and in that dark area, condition, and when it is raining, it becomes even much more difficult, right? Like just like let me share one example which we did just recently. We went on a ship, which is a long haul fishing ship. Long haul fishing ship goes very far away from the land. It goes into the far seas to do fishing. We wanted to apply AI techniques so that we could detect, like for example, the fishermen doing fishing. we saw that normally they do fishing during the night. It's during the night, and there's heavy water because the water keeps on flashing from the sea to the ship. Okay, so the water keeps on coming, and we saw that in the videos that the fishermen, while they are fishing, they're wearing raincoats and with some rain caps, boots, rain boots, all these, the full body is covered with things, and they are still working. So in that condition, it's dark and there are lots of noises in the image, so it's very difficult to do human detection. Actually, we wanted to do post detection. That is, who is standing, who is sitting, who is working, who is not working, how he is working, is he working very hard or whatever. Okay, we wanted to do these kind of detections, but it was very, very difficult because, one, it was very dark, and the other is because there were lots of noises. There's so much water, so much sea water is gushing into the ship. So not in a real condition, it's not like what we just saw. And let me explain one thing. What we did was single image deraining. There are two kinds of deraining. One is called single image deraining. That is what we did, and that is what many of the papers are doing. The other is video based. Okay, video based means you have multiple frames. Then of course you have more data because you have 30 frames per second. So actually you can look front and back and see how you can do deraining, right? Because then deraining becomes a little easier because you have more information. Okay, you have more frames, so you have more information. So that is also something which we could work on, but this is just the single image deraining. So that was the first question. The second question is about the GT. GT means ground truth. Of course, we won't be able to get the ground truth in real time. So ground truth is normally only used when you are training your model. Okay, training your model. When you're actually after you have trained your model and actually you have deployed your model, for example, in an autonomous car, then there's no need of any ground truth because you're not doing any training, right? Ground truth is for training. When you're doing inferencing, because normally deep learning, we have two parts, right? Two phases. One is the training phase, the other is for the inferencing phase, or the actual use of the model. So in an autonomous driving real application, the models have already been trained. So we don't need the ground truth. We are just using the models to remove the rain. Yeah, to remove the rain. But during the training process, we do need the ground truth. So normally what we do is we get the ground truth, that is the images of the outdoors or whatever, which does not have the rain, and then we either add the rain or we take real rainy images. So that is for training. So for training, we need ground truth. So as you asked, for real time means when you're using it. When you're using it, you don't need the ground truth. So we are not generating any ground truth. Yeah. Okay. I think I answered both questions. Any other questions?
Yes. Sir, I'm having one question.
Yes.
Like as you told, we can use this train model, and using this train model, you have detected like the fisherman. It can be detected. Okay, they are doing fishing and those things. So if we are using the trained model in drone, for an example, like we use cameras in drone, and when it will be there near the border area of India, and if anyone is coming inside, is it possible like using this train model, it can detect clearly whether who is coming inside or who is going outside? So it can be useful for security purpose as well, right?
Yeah, sure.
Can I add a small sort of addition to what Dr. Jugal has said?
Yeah.
Just related to that only. Most of the time in our security community, also in the security community also, we use satellite imageries for detecting the terrorist camp or those sort of targets. But most of the time, because of cloud, because of the condition of the atmosphere in India, because of cloud, the imageries are not clear. So
and even because of smoke or fog,
yeah, smog, fogs, clouds, we are not able to capture the correct image. So these kind of applications, will it be able to help in the satellite data, satellite imagery, producing satellite imagery?
Yeah, I believe, let me answer the first question about the border security. Of course, if you use drone, you can always detect whatever you want to detect. But the problem will be most of the drones don't have enough power for extended periods of time. So when we are doing GPU analysis or using GPU to do the detection, we have to be careful that it is low power. So once we have a low power version of whatever we are trying to do, because trying to remove the fog or the smoke or the rain or whatever, or the dust, I think in the near the borders is mainly there are lots of dust and lots of noises in the image because of the dust. So of course we can remove it, but we don't want to spend too much power in doing that. Then otherwise the drone will go out of power much faster than when it is already without the extra computation. So that will be one thing which we need to consider before we actually put it on the drone. As far as the satellite images are concerned, I think we can always do some kind of image processing using these kind of models, where we can remove at least part of the light clouds. I'm not sure about the heavy clouds. If the clouds are very heavy, or if the condition is very, very bad, I don't think we can do any reconstruction. But suppose the satellite images are coming constantly inside. Suppose we have one satellite image, for example, per minute. Then of course we'll have lots of satellite images, and maybe the clouds are moving away or coming back again. Then of course we can always have AI models which can reconstruct the whatever we are looking at, I mean the target location, by looking at multiple images from the satellite and removing whatever is in the as noises, whatever noises are in the images. I think it's always possible. Yeah.
So, sir, using this model, is it possible to process real time? Is it possible to get real time images?
Yeah, sure, we can get real-time images, but it always depends on what platform we are using. Currently, like for example, for the Jetson Nano, it's too small. Normally, like in traffic control systems in Taiwan, they have already switched to other platforms like Xavier or TX2, those kind of platforms. Yeah, so that platforms are much more faster, and that can always be used for real-time image processing.
Thank you, sir. So,
Yeah,
is
thank
there
you.
any other questions? We can take any one more questions if anyone have. Otherwise, we can finish the session. I think, sir, there are no more questions.
Okay.
Thank you so much. It was really interesting because the topic was, a bit different from what we were going through all the sessions. So it was really very interesting, and it was, more technically you went into. So we got more ideas also, what algorithms you have used, what are the, different activation functions you have implemented. So thank you so much, sir.
Okay. Thank you, Dr. Jugal. Thank you, everyone. Thank you for your kind attention. Thank you.
Yeah, thank you so much.
Version which we installed in Nano, but of course that is for another project.